Welcome to the walkthrough of Assignment 3 Part B for my CS5254 course in the summer of 2023. The objective of this part of the assignment is to learn how to synchronize beings in Middle-earth via a concurrent hash map and a fair semaphore that's implemented using the specific notification pattern. Videos describing the relevant topics appear as follows. The Java concurrent hash map is described here, and the specific notification pattern is described here. Please watch these videos to ensure you understand these Java synchronizers and patterns. Naturally, we'll cover these topics in class as well. In this part of the assignment, you'll enhance the Palantary Manager portion of the Palantary Simulator app from Assignment 3A, which implemented the Being Manager via the Java Executor Completion Service and Executor Service concurrency frameworks. Assignment 3B focuses on applying a concurrent hash map and a specific notification-based fair semaphore to the Palantary Manager, which is used to restrict the number of beings from Middle-earth who can concurrently gaze into a fixed number of Palantiri. The Palantary Simulator app is packaged as a project using the latest version of Android Studio. This app is written in both Kotlin and Java and demonstrates many Android capabilities. For the purposes of Assignment 3B, however, you only need to be aware of the following three directories. Simulator Manager's Palantiri Concurrent Map Fair Semaphore, which contains the skeletons you need to fill in, is described below. App Source Test, which is a set of unit tests that exercise many Palantary Simulator features and can be used to help test the functionality you implement for the assignment. And finally, App Source Android Test, which is an Android Studio instrumentation test that runs your app automatically. You'll also need to integrate your enhanced solution for the completion service folder from Assignment 3A into the latest and greatest completion service skeleton and use it as the implementation of the Being Manager for Assignment 3B. Of course, make sure to address all my comments from Assignment 3A into your Assignment 3B solution. To compile this code, you'll need to use the provided Android Studio project. You can run this project by clicking the green Run App button in the Android Studio IDE, which should automatically select an Android emulator to run, assuming you have one created. The app is designed to work with Android API Level 33, so you need to select an emulator that uses API Level 33. If you don't already have an emulator created, you can create it by clicking on the ABD Manager button in the Android Studio IDE. You'll need to modify several files containing the skeleton Java code by completing the to-do you fill in here task to provide a working solution. Please don't change the overall structure of the skeleton, just fill in the to-do tasks and don't delete the to-do tags. In particular, you need to finish implementing the following to-do tasks for this assignment in the concurrent map fair semaphore folder. First, you need to complete the to-do task in the concurrent map fair semaphore manager.java file in various methods to implement a Palantary Manager via a concurrent hash map and a fair semaphore. Undergrad students need to complete the to-do tasks in the fair semaphore mo.java file to implement a fair semaphore using Java's built-in monitor objects. Graduate students need to complete the to-do tasks in the fair semaphore co.java file in various methods to implement a fair semaphore using Java Ranchlet locks and condition objects. You'll need to also complete the to-do task in the student.kt file to set the type field to either graduate or undergraduate, depending on which version of the assignment that you're implementing. Your app will be considered correct if it passes all the unit instrumentation tests and all beings successfully complete all their n iterations. A correct simulation should restrict the number of gazing beings to the number of Palantiri. In other words, if there are 4 Palantiri in the simulation, then only 4 beings should ever be gazing on the screen at a time. When the simulation is running, the app view will display visual feedback to show Palantiri and being states, as well as the progress of their gazing iterations. If your assignment implementation is correct and doesn't throw any exceptions, then the app title bar labels will appear green when the simulation completes. However, if your solution is not implemented correctly or throws an exception, then red title bar labels will be displayed when the simulation completes. Skeleton code for this assignment is available in my GitHub account. Now that you've set up your GitLab account, you can pull the skeleton code into your repository, read it carefully, and complete the to-do markers. The unit tests in the App Source Test folder are provided to increase our collective confidence that your implementation is working as expected. It's essential that you use the Android Studio GUI to run these unit tests locally on your computer, as described here and shown later in this video. As usual, testing only demonstrates the presence of bugs, not their absence, so don't rely solely on tests to detect problems in your code. In particular, I'll also provide videos that walk through frequently made mistakes that you should address. Please address these issues prior to your submissions to streamline our programming assignment review and assessment process. This part of the assignment is designed to deepen your understanding of synchronizing multi-threaded programs using the Java concurrent hash map and the specific notification pattern. The fair semaphore implementation is a bit tricky, however, so please start early and come to office hours if you have any questions. Now that we've talked about the specification, let's go ahead and take a look at the skeletons. As you can see, the place to focus on is concurrent map fair semaphore. That's the folder within the skeletons that I have uploaded to GitHub. And as you'll see, there's a couple of things you got to look at. I'll start by just giving you the simple interface. This is the fair semaphore interface. So here you can see fair semaphore is an interface, and it's just got 4 simple methods: acquire uninterruptibly, which won't be interruptible; acquire, which can be interrupted; release, and available permits. Those are the 4 things that you'll have to implement. And then, as I said, there's a couple different ways to do this. So I think what we'll do is, first we'll take a look at the manager that's kind of driving all this stuff. Then we'll take a look at the skeletons for the fair semaphore. That's where all the complexity lurks in this assignment. So you can see here, we have a concurrent map fair semaphore manager. It's going to have a field called M available Palantiri, which is a fair semaphore. Undergrads will implement one variant, grads will implement another. We'll see how that works in a second. And then we've also got our concurrent map, which has an interesting comment. You can ignore that. For the most part, it's already solved for you, but it's a weird bit of inconsistency between different versions of Java. The concurrent map will be implemented using a concurrent hash map. There are different kinds of concurrent maps, but you're going to be using a concurrent hash map. And it's going to be a concurrent hash map that maps Palantir to Boolean, where the Boolean are used to keep track of whether the Palantir is in use or not. That part should be very familiar to you. We've done that a gazillion times before. Here is the build model. Factory method. This is the thing that does the initialization of the internal state of those fields. And you'll have to create a new concurrent hash map. That's pretty easy. Iterate through the list of Palantiri using the same techniques you had before. Initialize each key in the hash map with true to indicate it's available. You've done that before as well. And then also initialize the semaphore, which is the third field we talked about, using a fair implementation. And in this case, the grad students must say, new fair semaphore CO for condition object, and the undergrads have to use fair semaphore MO. But otherwise, it'll look the same. You're just changing the kind of semaphore. And as usual, we make this easy by factoring out commonality by using the fair semaphore interface, and we just make a different implementation. Okay, so far so good. Here's the acquire method. Now, acquire is actually, it's very subtle. It's really simple in terms of code. There's not much code at all, but you have to think carefully about sort of why the code does what it does and how you write it. And I'll explain it here momentarily, and then you'll have to think about it some more. So the key thing to remember is unlike every other example that we've done with the Palantiri manager, we'll have no explicit synchronizers in acquire or release at all. So if you think back to the, things that you've written, we've used spin locks, we've used reentrant locks, we've used, I think we may have used synchronized statements maybe, we've used stamp lock, that's what we're doing now. All those things you had to explicitly acquire and release something one way or another, right? Lock, unlock, acquire, write lock, try to upgrade, all that kind of stuff. In this case, we're not going to have any synchronized statements or any synchronizers in this method at all. And when I say there should be no synchronized statements, I don't mean, define a reentrant lock and use lock. I mean, there should be no synchronizers, explicit synchronizers in this code. This will all be handled by the magic of concurrent hash map. And as we'll talk about later, concurrent hash map has this really cool method, and I give you a hint when I say atomically replace, hint, hint. There's a method called replace, and replace works very much like compare and swap. If you remember compare and swap, we talked about when we discussed spin locks. And the idea with replace is you say, replace this key, which will be a Palantir, obviously, to this value if the current value is that. So that's what you're going to have to do. You're going to have to use the replace method, and you're going to have to do this. You're going to have to try to do this atomic replace. If it turns out that the value is not what you would like it to be, then replace fails. If it turns out that the value is what you want it to be, replace succeeds. And when it succeeds, it does the atomic swap. Atomic set, really. Atomic replace. So it's really, really simple code. We got to think about how it's going to work, and you have to think more deeply about what does it mean to do this. Now, the thing that's kind of funky and tricky about this is concurrent hash maps, the operations in concurrent hash map, like replace or put or whatever, they always do the minimal amount of locking to get the job done, but they never, ever, ever lock the entire data structure. The entire data structure is never locked. And that means if multiple threads are calling into acquire and release, and you have lots of threads and they're calling acquire and release in all kinds of interleaved orders, there's no way that you can be sure that other things in the hash map haven't changed while you were busy doing your one thing. And this becomes very important when you write this code. So even though there's no synchronized, explicit synchronizers in this code at all, you're going to have to think carefully about how to ensure that you always successfully end up doing the appropriate update to the map. And there's a couple things that will help guide you here, right? One of which is you have a semaphore, so you can mediate access that way. So remember, what is the purpose of the semaphore in the Palantiri manager? What role is it playing? And this is the case for every single one we've done. What is the semaphore trying to do? Joe? To track the available Palantiri. So assuming you've written your semaphore correctly, right? Assuming you have your fair semaphore, and it works right, that means that there should always be a Palantir available, right? Because otherwise you never would have acquired the semaphore. If you said, let's say the max number of concurrently gazing beings could be 6, right? So the count will be 6. Your semaphore will make sure that there's never 7 things trying to acquire stuff. So there should always be an open, available element in the hash map. However, because of the fact as you iterate through this thing, you don't really know what other threads are doing concurrently. A single left to right pass, using the word left to right sort of loosely, a single pass through every element in the hash map may not actually be sufficient to find the available Palantir. And so you're going to have to think carefully about how to write the code here in order to make sure that you don't do a single linear pass and then through tricks and non-determinism of concurrency end up appearing to find no Palantir, even though there is one there. And that's really subtle. The solution is absolutely trivial, but you need to think about it. So I will let you ponder and puzzle out how to do that. Anyway, this code is really, really tight and concise, but it's subtle. Here's release. Release is actually much, much, much simpler because we don't have to worry about any of this kind of stuff. So what we're going to do here is, once again, there should be no synchronizers in this code at all. No synchronized methods, no lock, no unlock, no stamp lock, no nothing. Definitely no synchronized, though. Don't do anything that involves synchronizers. And all you're going to do is, after you do some sanity checking to make sure you're not trying to put a null Palantir back in the map, you're going to put the true value back into the map and release the semaphore. So indicating that there's another thing that's available. And so when you put true, that just means you update that Palantir to be true. It used to be false. Now it's true. True meaning it's available. That is a really, really simple piece of code. That's actually going to look very much like what you did before. The difference is, again, there's no need for explicit synchronization because the method that you use to update the map will have the synchronization built into it. So you don't have to worry about it. But again, always keep in mind that any operation on a concurrent hash map does the minimal amount of synchronization to do its thing, and it never locks the entire map. Okay, so that's the overview of concurrent map fair semaphore manager. The hardest method there is acquire, and that's short, but you'll have to think about how it works. Let's now go take a look at the fair semaphore skeleton. And this is the one that the undergrads have to do. This, as you'll see, will use the specific notification pattern. So here's some of the stuff you'll have to do. You'll have to define the field that's used to keep track of the number of available permits. Now that you've done assignment 3B, that should be real easy because it's the same thing. But make sure you do it the same way, correctly. Then we have this waiter class. As you'll see, this is kind of an interesting class. It just has a single field called mReleased. That's all. And you'll see that this is what is going to be used to keep track of the waiting threads. We also have a wait queue, and I recommend implementing this as a linked list. You could do it as an array list as well, but linked list probably works pretty well. And notice it's just going to be a good old naked linked list, no synchronized linked list or concurrent linked list or concurrent queue or anything. It's just a linked list. And we're going to rely on the intrinsic lock, the monitor lock of the fair semaphore MO object to give us any synchronization we need to protect the permit count and the linked list. Your constructor needs to initialize the fields properly to get them set up. Acquire and acquire uninterruptibly. I gave you acquire. So this is what acquire looks like. And we first do a little sanity check here, and then we do this stuff. And acquire uninterruptibly is what you'll have to implement. It looks actually quite a bit like stuff that you've done before, but you have to figure out how to implement it. And make sure that you use a loop and you ignore interrupted exceptions, but you do, of course, keep track of the fact that they occurred, just like you did before. Okay, so obviously the devil's going to be in the try to get permit method and the wait for permit method and anything else that they may call. As we'll see in a second, try to get permit is the happy path. This is the fast path where no blocking is necessary. So that, of course, is going to have the right synchronization in it. You're going to have to use a synchronized block here if you're doing the undergrad version. And what it's going to do is it's going to acquire the lock, and it's going to check to see if the queue is empty and if permits are available. And so if the queue is empty and permits are available, then that's the fast path. It will go ahead and return, it'll go ahead and do its thing, and it'll return true, and you're done, right, at that point. So that's the happy path. Now things get interesting. This is the wait for permit method, and this is the one that has all the nitty-gritty details of the specific notification pattern. And so for this, what you'll do is I would recommend you go back and you watch the video that I did earlier on specific notification, and that's where you're going to implement the logic. And this code, again, it's not really long code. It's actually maybe a screen or two full of code, depending on how much you comment it. But it's really subtle. And so that's where you have to figure out how to wait for a permit, which is going to involve, making the waiter object and correctly putting it into the queue, into the linked list, and handling exceptions and all the stuff that we talked about when we talked about how acquire was implemented in the video. So that's where that stuff goes. Release is then the implementation of the discussion in the video about giving back a semaphore into the, or releasing another waiting thread if there is one using the specific notification pattern. And remember, there's sort of two cases here. One case is where there are no waiters, which is again the fast path. And so you're just going to increment the permit count and you're done. The other case is there is a waiter, at least one waiter, in which case you're going to take that guy out of the queue, out of the linked list, and you're then going to notify that thread to wake up and run. Remember, as we talked about in the other video, there's an optimization that happens in that case where you're going to essentially not do anything with the count at all if you're going to wake somebody up, because it's a wash, right? You're incrementing, it's going to decrement, just leave it where it is, right? It makes it easier that way. So that's going to be release. And then available permits, this is a no-brainer, but just go ahead and replace 0 with the appropriate field that's keeping track of the permit count. Okay, so all the complexity in this method really is or in this class is really wait for permit and release. That's where you've got to really sit down and think carefully about what the heck is going on. But it's super cool. So by the time you get done with this program, you will have a much deeper understanding of synchronization and how it works and why it's important to protect shared mutable state in such a fundamental way. Okay, so that's the undergrad version. Here's the graduate version. The graduate version has the same semantics, just is implemented differently, and there's a few extra things we get to do. So we're going to use a condition object here and reentrant lock. So you have to make the field that keeps track of the permit count. No surprise there. The waiter class is a little different. It still has the mReleased flag, but it's got a couple of other fields too. It's got a lock, which is going to be the lock to protect mReleased, and it's also got a condition object, which we'll use to wait notify threads appropriately. So you got to add those things. Pretty easy. Always remember when you're defining fields for things like reentrant lock and condition object, always make sure the fields are the interfaces, like lock and condition. So don't say reentrant lock, don't make the field be a reentrant lock, make the field be a lock that in its constructor is initialized with reentrant lock. Same thing is true for condition. You'll also need a monitor lock since we're not using the built-in monitor locks here. So you'll have to make a reentrant lock to protect the critical section of the Fair Semaphore CO. Here's the constructor. You're going to have to initialize the fields in the class. A little bit different from the other one, but not much. Once again, we have acquire and acquire uninterruptibly. Those are very much like the ones the undergrads do. This one is a little different. So we're going to have a method here called try to get permit. And if the return value is true, the monitor lock has been unlocked. Otherwise, it's still locked. And this is playing off of the fact that the way that things work with Java conditions objects and reentrant locks is you don't have a strict scope locking idiom there. You can control the way those things get used. So we have try to get permit. That's the fast path. Try to get permit unlocked, which makes some assumptions about the monitor lock being held. And then here's wait for permit and release. And as you can see, once again, that's where all the complexity is going to lurk. The code is very, very similar. The main difference, again, is that because the grad student version doesn't use monitor objects, but uses condition objects and reentrant locks, there's just ever so much more syntax to make sure you acquire the locks and release them in try finally block kinds of things and so on. So the basic, if you took a look at the two things side by side, you'd be able to tell almost one-to-one that they map, that just a bit more syntax here. And there's a few other little optimizations that you have to be aware of as well. And then finally, you have to implement the available permits accessor method to return the count. So now that we've walked through the specification and skeletons, it's time to run the unit tests. As usual, we'll click on the right button in order to get the tests started. And you can see they're going ahead and instantiating. It'll take a little while to get them up and running, but once they're starting running, you can see that they have both normal tests and stress tests. Those are kind of black box tests. And then there's a whole slew of white box tests. The tests are cumulative as always. So there's actually quite a large number of tests here. Make sure that you copy your solution from previous assignments so that those tests will pass. You'll be graded based on the number of tests that pass in total, not just the ones for the current assignment. So you can see there's a total of 185 tests. There's this warning here. You can ignore that warning. It's a little bit annoying, but it doesn't mean anything that's harmful, so just ignore that for now. And if you have any questions whatsoever, please let me know. Don't forget to take a screenshot of the tests that run so I can get a glimpse of what's happening, why you might be having some problems, and I look forward to seeing your solutions.